In the previous section, we talked about differentiating inverse trig functions, and really that was just a lead up into what we're going to do now, and we're going to integrate using the inverse trig. So we're not actually going to integrate inverse trig functions, but we're going to integrate using those patterns that we learned when we differentiated them. So we have these three, and these are the ones that we really have to worry about integrating. Okay, and initially it's a matter of recognizing these patterns and knowing these patterns really well from our work in differentiating in the last section. So just like any other integration rule, you really have to know the differentiation rule first to be able to recognize this pattern and achieve the pattern and then do the integration. So we need to know these patterns very well, and what we're going to try to do is match the problem that we have to one of these patterns. Okay, so in this first example, we can see when we take this problem and we look up at our three choices, it looks the most like this, right? So it looks like we're going to end up with an arctangent when we do this integration. So we have a constant squared plus some function of x squared, and we can really write it just like that if we substitute u equals x and a equals 3, and we can match that pattern exactly, right? And we need to make sure when we do du, we get just dx, so that 1 in the numerator works out well for us. We're good there. And then we just fit the pattern. It's 1/3 arctan of x over 3 plus our constant of integration. Okay, so that's obviously a pretty straightforward one, a problem that fits the pattern really directly. We have another one here. And again, when we start with this, we look at this and we say, okay, well, which of those patterns does it look most like? So if you look above on your notes, we have the square root, some function of x minus a constant. Right? So if I compare that, these are the two here that have a square root in the denominator. The arcsine rule or integral is a constant squared minus a u squared, some function of x squared. That's not what we have here. We have a function of x squared minus a constant squared. But you see that we also have this absolute value of u, and ours doesn't fit that quite well, or at least doesn't fit it well quite yet, I should say. So let's try to match this part up here. All right. So I noticed that if I let u equal e to the x, then this e to the 2x is u squared, so that's good. Sorry, you can't see that. So I let u equal x, then I get u squared is e to the 2x. If a equals 1, I get minus 1. And then the du gives me e to the x dx. So I'm going to rewrite it this way. In order for me to get this e to the x in the numerator, e to the x dx, I need to have an e to the x in the denominator that essentially cancels that out. So if I rewrite it this way, now I can use these substitutions, and it fits my arcsecant formula. Once I do that, I can simplify that. I just get my arcsecant. All right. So that's one that it was really close to the arcsecant integral, but I needed that e to the x over e to the x to give me this absolute value of u that you see here. All right. So again, this one fit directly. This one took some work to make it look, but it was a pretty small change we needed to make because we could see that this part here almost fit the arcsecant, and we had that part inside the square root fit, but we needed to figure out a way to get that du over u here. And the e to the x works out well since du and u are the same thing. All right? So in a general sense, if the integrand doesn't match any of the three formulas that we have, we need to try some things to make them look. So these are make them look like one of those functions. So these are the most common. If there's an addition or subtraction in the numerator, separate that expression into separate expressions. So split it up if you have addition or subtraction in the numerator. If the numerator is a higher degree, do the polynomial long division. Then you'll get some polynomial with a remainder. You can deal with the remainder separately. And then complete the square in the denominator is another one that we'll take a look at an example. So we'll look at a few examples of these types here on the next page.